this section is about intrinsic camera calibration, right? So I'm going to quickly run through the theory bits of this as well, and then run through a quick demonstration. Right. So a really important thing when dealing with cameras is really understanding how camera projection works. Basically, what a camera does is it takes 3D objects, right? So when I take a picture, or even right now through the webcam, what's happening is I am a fully 3D object, but you guys are seeing it on your computer as a 2D flat object, right? So what a camera really does is it takes 3D objects and projects it onto a 2D plane, right? So really understanding how that happens mathematically can help you, especially in robotics, do a lot of things. Like even, for example, take a 2D image and then project it back into 3D space, right? To understand where objects are in 3D, right? So really understanding how images are formed is super important, right? So part of your pre-work that I gave you guys was on the pinhole camera model, right? So the pinhole camera model is a very simple and basic model of how camera projection works, right? So there are more complicated, mathematically complicated camera models that take into account things like distortion in your image and things like that, right? But this is kind of the simplest mathematical model that you can make for a camera, right? So the Wikipedia page that I gave you guys is pretty easy to understand and has like pretty simple diagrams. So I'm going to use that to kind of explain everything, right? So if you look at this image kind of sets up all the important coordinate frames that we have to worry about, right? So this is where all the knowledge from tutorial 1 is important about how coordinate frames work and stuff, right? So there's really two important coordinate frames that you have to think about when you're dealing with a camera, right? One is what we call the camera coordinate frame, right? Which is this coordinate frame given by x1, x2, and x3, right? So this coordinate frame is defined at the aperture of your camera, right? That is the small hole in a camera through which light kind of goes in, kind of like the iris in your eye, right? So imagine a coordinate axis defined at the aperture of your camera, right? That is what we call the camera coordinate frame, right? So it's given by x1, x2, x3 here, right? So everything out in the real world in 3D space can be defined relative to that camera coordinate frame, right? So imagine there's a 3D point out in space called P, right? Imagine it's, say, the top of this bottle or something like that, right? So the top of this bottle can be defined in three coordinates given by x1, x2, and x3, right? Defined relative to x1, x2, x3 coordinate axis. Is that clear? So P is a real 3D point out in the world, right? The second coordinate frame that you have to really think about is what we call the image plane, right? So the image plane is basically the 2D plane where this 3D point is projected onto, kind of like imagine sort of like a shadow on a wall or something like that, right? A 3D object puts like a 2D shadow on a wall, right? So this light gets projected onto a 2D image plane, right? So the coordinate axis in this 2D image plane is what we call the image coordinate frame, right? So that's what's given as y1 and y2. So that's a 2D coordinate frame. So this 3D point gets projected on this 2D plane, and that point where it gets projected is what we call Q, right? It's basically the image point, right? On top of that, there are a few more important things to think, kind of important terms to know, right? The distance between the image plane and this camera coordinate frame is what we call the focal length, given by f, right? And this axis, x3, is what we call the principal axis, right? And the place this principal axis intersects with your image plane is called the principal point, right? So in this image, the principal point is R, right? So that's really how the projection works. So to understand the relationship between the 3D point P and this 2D point Q, which is ultimately what you get in your image, there's a bit of a simple mathematical derivation of it, right? So this image plane really corresponds to like the sensor in your camera, right? So light falls onto a light sensitive sensor in your camera, right? Which is what forms the final image in the case of a digital camera on a digital image, or in the case of like an old camera on a light sensitive film, right? So that's really what the image plane kind of corresponds to. It's something inside the camera, and everything in front of this is out in the real world, right? So to understand the relationship between these 2 points, what we can do is we can look at this diagram from the top, right? Imagine we are looking at this diagram from the x2 axis, right? Imagine we are looking at it from the top like this. That representation is what's given in this diagram, right? So, sorry. You can see if you compare these 2 diagrams, this x1 axis is now pointing down like this. The y1 axis is now pointing down like this, right? So we are really looking at this from the top. Okay, so when we look at it from the top, you can see that this is your 3D point and Q is your image point. If you look at these 2 triangles from like basic high school maths, we know that these 2 triangles are what we call similar triangles, which mean they share the same angles, right? These are alternating angles. This is a 90-degree angle, and this makes this angle also equal. So since they're similar triangles, that means the ratio of this divided by this is the same as the ratio of this divided by this, right? So that's how you get this equation, minus y1 over f equals x1 over x3, right? So if you subject y1 here, you get this equation. So y1 and y2 is the image coordinates corresponding to this 3D point, right? So by the way, it's simple y1, y2. The capital Y1 and Y2 are the names of the axes, right? Simple y1, simple y2 is the actual coordinate value. So what this shows you is, this relationship shows you is, if you have the 3D points defined relative to capital X1, capital X2, and capital X3, you can convert it now to where it actually falls on the 2D image plane, right? Which is point y1 and y2, right? So we just derived the equation for y1. To derive the equation for y2, you have to just take the same image and look at it from this side rather than from the top. You look at it from this side, and you'll get a very similar equation using the same similar triangle logic, right? From that, you end up with these 2 equations for y1 and y2, and when you put it into kind of a vector form, you can get this equation, right? So what this shows you is basically you're getting the mapping between your 3D points to 2D points, right? Is that clear? Any questions? Okay, one more thing, you can notice that the image kind of gets inverted, right, when the projection happens. If you have a image like if your real point is over here, your image gets inverted here. If you had a point over here, it will get inverted over here. So the image that's actually formed in a camera is upside down, it's inverted. But in a digital camera or even a film camera, what you do in a film camera, it doesn't matter, because when you print the images, you just can turn it the other way around or whatever. But in a digital camera, you also digitally kind of convert the image upright, right? So when you add that correction, what you're doing is you're rotating the image by 180 degrees, which is why the final equations doesn't have this minus sign, right? So the final equation kind of looks like this, right? There is an additional thing I want to talk about, and that's what we call the camera matrix, right? So if you look at this, right, I'll quickly write this down. Again, this will be there in the recording, so also if you want to write this down, you can write this down. So what we saw was, we have this equation, right? you have 2 points y1, y2, and you have f divided by x3, x1, x2, right? You can actually get this same set of equations, right? These are the two equations, right? By writing all of this in a matrix form like this, right? Actually, do you guys remember the homogeneous matrices that we used last time? We can use a similar homogeneous matrix and get this equation. Right? You can multiply this out and see that you get the same what do you call it, final equations, right? So actually in this case you will get this will be x3, right? Sorry, this won't be y1 and y2. Give me a sec. I made a small mistake. Hold on. I'll actually work backwards from this. So I have f 0, 0, 0, 0, f 0, 0, 0, 0, 1, 0, and I'm going to multiply this by x1, x2, x3, 1, and what I'm going to get as the output, if I do this multiplication, is f into x1 and then f into x2 here, because everything else is 0, and then 1 into x3, right? So this is going to be the output of this multiplication, right? But what is my final image plane values? It should be f x1 divided by x3, f x2 divided by x3, right? So since this is a since you want to put this in a homogeneous form, right, what you do to create a 1 here is you divide this element and this element by x3, right? Because if you do that, what you get is correct, right? So if you use this matrix and multiply a 3D point, you will get these values, and if you take these values and divide this and this by the third value in your output vector, what you're getting is y1 and y2, right? Which is the same as basically these two equations, your final output, right? So this matrix can actually take your 3D point and convert it into your 2D point, right? So this matrix is what we call the camera matrix. Cool?
One second.
Yeah.
So in the right side of the equation,
Mhm.
then we have to divide that by x by 3. Sorry, x3.
Yeah. So so if you take the right side and divide by
Like the camera matrix, so
Yes.
we have to divide it by x3 to get.
So
the
yeah, I mean you can do it in different ways. You can divide your output vector by x3, sorry, your input vector by x3, or you can just do this multiplication, get this output vector
Okay.
just the way it is, and then do a separate operation and just divide everything by x3.
Okay. So
Right?
that means the camera matrix does not change.
Yeah, the
That
camera
is
matrix doesn't
okay.
change, right? Because the camera matrix doesn't depend on the shouldn't depend on your 3D point, right? It's something that's intrinsic to the camera, right? If you look at it, the reason why we are doing this is because now the camera matrix, whatever these points are, right, is independent of those points. It only includes focal length in it, right?
Yeah.
So then we can define a camera matrix for a particular camera without having to worry about what the 3D point or the 2D points are, if that makes any sense. Cool?
Yeah. Okay.
So another thing gets added onto the camera matrix, and this basically, if you looked at this diagram, you assume that the principal point is at the center, right? As in, the principal point is always going to be at the center. You assume that the coordinate frame is defined at that principal point, right? But the thing is, for example, in MATLAB, you probably notice that the images are actually indexed. So if I take an image, images are indexed from this point, right? Not at the center. So the center coordinate, for example, would be, in this case, 2, 2. Right? So in a large image, for example, like the images that we saw, there were lots of grids, right? So for example, if it's a image of size 1080 by 720 or something, right? Your central pixel will be at 540 by 360, right? So when you're indexing the image, your coordinate frame is actually defined here in MATLAB, not at the principal point, right? So 0, 0 is not here. It's usually you have an offset, right? So all you have to do then is, it's just remember translations that we learned last time. So all that has happened is this coordinate axis has been translated here, right? That's all that has happened. So all we need to do is we need to find the principal axis coordinates relative to our coordinate frame and just shift our answer by that, right? So we just need to add a translation. So our final y1 and y2, if there is a shift in your principal axis, is going to look like this. Cool? Is that clear?
Yeah, but when do we add that shift?
Yes. So what we do then is we just change our camera matrix to include px and py here as a translation.
Oh, okay.
Right? So our final camera matrix is going to look like this. Sorry. By the way, hope you guys are like writing this down because it's not in the pre-work.
Can you just zoom it like?
Yes, that's another. So you have f0 px 0 0 f py 0 0 0 1 0. Cool. So this is what we call our camera intrinsic matrix or camera matrix. So what we do when we do an intrinsic calibration is we try to find these values. We try to find the focal length and we try to find the principal point of your image, right? Relative to the coordinate frame of your image, which is usually at the top right corner, right? I think in OpenCV it's at the bottom left corner, right? So just whenever you're using any sort of library, whether it's OpenCV or MATLAB, just be aware of where the image kind of coordinates really start from. But yeah, so the calibration process helps you figure these values out, right? So that's really what intrinsic calibration really means. Any questions?
Can you just go back to that page that you are still copying?
Yep.
Yeah, just 2 minutes.
Sure. Let me know when you're done.
Yeah, done.
Okay, cool. Is everyone else good to keep going? Okay, I'm just going to assume your silence means yes. Okay, so what we're going to do now is use MATLAB's inbuilt camera calibrator app to just do this calibration really easily and try and get that camera intrinsic parameters, right? So basically you need to make sure you install your camera calibrator app. You can do that by, you can go to the section called apps in MATLAB and you can say get more apps or install app. Usually if you have the image processing toolbox, the camera calibrator app comes along with it. So you open this up. In your pre-work, I asked you guys to go through a video of how to do it. It's fairly straightforward. You say add images, right? And in your lab 2 material, in under question, we are on question 3. I've given a bunch of images. I've given you 15 images. So you add those all and you say 35 millimeters for the size of a checkerboard, right? So what the calibration app does is these checkerboard images that I've taken, right? I printed this out, right? And I designed this calibration. It's called a calibration target, right? And I know the size of these squares because I printed it out on my printer, right? So I know that each of these squares are 35 millimeters long. So what the camera calibration app does is it detects these these corners, right? And since I've said it's 35 millimeters long, it tries to, and I've given it 15 images, so it tries to use those 15 images to work out the focal length and px and py required for me to translate these edge points to 3D space at a 35 millimeter distance from each other, right? So it kind of works in backwards. It knows what these points are. It detects it in the app, and then since we said it's 35 millimeters, it projects it out into space, right? From the 2D image, right? Kind of the opposite of the explanation I gave you guys on Wiki, which was taking a 3D image and projecting it in 2D. It takes the 2D image and reprojects it back out, does the reverse of those equations, right? and through an optimization process figures out what's the best focal length and best px and py required to give that 35 millimeter distance between each of the checker points, right? And it averages it out over 15 images, right? So when I say okay, right, it loads the images. And it says detecting checkerboards, right? So it's detecting the checkerboard in the images, right? And you can see here what it has done is it detected each of the edges here, and it's defined the a coordinate frame for the checkerboard, right? If you can notice, this checkerboard is also asymmetrical. You can see that there are 4 squares on the top and only 3 squares at the bottom, right? This allows it to know where the coordinate frame kind of starts in each of the checkerboards. So even if I rotated this slightly differently, it would know, right? So then I click calibrate, and then it does the calibration, right? And gives the result here. So here in the bottom you can see, like I said before, it has reprojected into 3D space, right? Purely using 2D images, and the size that I said each of these squares are, right? So you can see that the images have been projected out, and here you can see something very important called reprojection errors. So what the reprojection errors are basically, what it does is, now that it has estimated the focal length and the px and the py, it imagines that it didn't have the 2D images, it only had these 3D images, and then what it does is it reprojects it back into 2D images, and then it compares it with the original checker points that it detected and sees whether they kind of overlap with each other, right? And there is an error between that, because ultimately this is only an estimate, right? So you can see this is the error between those reprojected points and the original checker points of the image. So it has reprojected it using its initial guess of the camera intrinsic parameters, and gives you an idea of what the errors look like. From that, you can kind of pick whatever images you feel are like outliers out of the images that you have, that don't really kind of represent all the other images. So you can see here that there is one error that's a bit higher than everyone else. So what you can do is you can select that, you can drag kind of a limit that you want your reprojection error to be. Generally, I think if it's like under 0.15 it's or 0.1, it's generally good. So but since this image here, image number 7, is clearly an outlier, what I can do is I can select that and then go here on image 7, and there's an option to say remove and recalibrate. So I'm going to remove it and recalibrate, and you can see that the overall pixel error has gone down now, right? And what you can do after that, so that's really up to you depending on your data. You can, if you want, get rid of outliers when you're doing the calibration, right? If there is like 1 or 2 images that don't kind of fit in with the rest of the images, you can get rid of them, right? And then what you can do finally to get the final result, there's an option that says export camera parameters. When you click that, it will export the camera parameters back into your MATLAB workspace. So actually hold on, let me clear my workspace first, right? And then what I'm going to do is say export camera parameters. I say OK, and you can see that the camera parameters will be in your workspace now, right? And a little summary of those is also given out here on your command window, right? So here it has estimated basically these parameters. So you can see that there are a couple of parameters here that we didn't really discuss, like radial distortion, tangential distortion, all those kind of stuff, but you don't have to really worry about those. Those are for more complex camera models. Since we only learned the pinhole camera model, when you double click this, you can see all the parameters that you really want, right? Like focal length and principal point, right? You can see it here. Cool. So how you access this? So for example, if you want to save this, you can right click on this and say save as, and you can save it as a .mat file, so that if you want it later, you can load it back, right? So you don't have to calibrate the camera all the time. You do it once, you save it, and then when you want, you can load it back, right? Any questions regarding the calibration process? Nope. Okay, cool. So then we're going to do the second part of that question, which is super important, which is to take a 3D point and project it to a 2D point, right? So to do that, I'll just open up the answer. Right. So if you notice in your camera parameters, your output, you can see that you have your two principal point values, right? But you're also getting two focal lengths, right? But I just explained to you guys how that's just one focal length, right? But again, for more complicated camera models, because of distortion in the image, there's always slight distortion, there's actually asymmetrical focal lengths, right? Which is why there are two focal lengths here. So when you're actually doing question number 2, you have two options. You could either just add the two focal lengths and divide by 2 and kind of get the average of it. Or I think a better solution, honestly, is treat them as two separate focal lengths. I'll just call it fx and fy. And so what I've done here is I've defined the principal point values px and py. I've taken those values from the final result. So by the way, these values are different to the final result I have, so I'm just going to copy paste it. And then if for focal length I have two values. If you want, you can just add those two values and divide by 2 and have a single value. But I'm just going to, just to be more precise, use two values. And I'm going to have fx and fy here. So k is a transformation, camera transformation matrix, right? But you can see here I haven't included the 0, 0, 1 here. Sorry, the 0, 0 line here, right? I've just taken this part. Actually, usually when you define the camera matrix, it's this part. It's a 3 by 3 matrix, right? This 0, 0, 0 is just added for the for the multiplication to be better, for the multiplication to work. So if you can just change that in your note, basically your camera matrix should just be the 3 by 3 matrix, which is f0 px, 0 f py, 0, 0, 1. Sorry. Yeah.
Then even that x matrix should be x1, x2, x3.
No. So for the multiplication to actually work, you need a homogeneous form. So you need to convert this camera matrix and add this column of zeros, right? So what I've done here is I've multiplied it with an identity matrix of size 3, 4, right? So when I say I 3, 4, right, that should give you something like this, right? So if I just multiply my k with this, I would get the correct size. But like for definition's sake, what a camera matrix is just purely that 3 by 3 matrix without the zeros. But when you're doing the final projection, you need to add the column of zeros for the mathematical multiplication to work, right? So
okay, so it's a bit confusing.
Yeah.
Okay, k is 3 by 3.
Yes.
But for multiplication, I need to add the extra row.
Yes.
Extra column.
So for the projection, final projection is the same, right? This is your final projection equation, right?
Okay.
So yeah, for definition's sake, this is what camera matrix is, right? But yeah, I mean, it's just a column of zeros. Mathematically, like again, it's not really. I mean, it's just imagine you multiply with the identity matrix of 3, 4, and you're kind of manipulating the matrix a bit, just adding a bunch of zeros, right? So I've said k into im into xcam, right? So xcam is a 3D location with 1 added to it because we are doing it in homogeneous space, and then your output vector is a 3 by 1 vector, and if I divide everything by the third element, I should get the final output values. Any questions? Shall I try to kind of make this a bit more mathematically precise, I guess? So, sorry. fx1 plus px fx2 plus py x3 is equal to f 0 px 0 f py 0 0 1, right? This is your camera matrix K. Multiplied into x1 x2 x3 1. Is that better? This is a 1, right? So this is like a identity matrix with additional column of zeros. Cool. And then your final answer, you just have to divide the first element and second element by x3. Okay. So you can put this under camera projection or something like that, right? Okay, so all we've done is taken all that and done it in a script, and when you run this, it should give you your final value. So there's 3D points maps to a 2D point on your image given by these two values. You can see there are point, like it's a float, but in your image, it'll obviously be some sort of integer value, right? Because you have the grid, obviously you can't have in between pixel values, right? So you'll have to probably round this off to get the actual pixel values that you want, right? Okay, any questions about this?
About this two focal lengths.
Yes.
In the formula, there's only one. In the matrix thing, there's only one focal length.
So this, yeah. So what I've done is I've actually.
Not to okay. In the previous thing, you told to average that, but now, how we get like two values?
Yeah. So the reason you get two values, if you hold on, let's go back to the wiki page. Where was that?
Oh no. Like I know like why we get two focal lengths because
Yes.
of the distortion.
Yeah, because for example, this image plane could be at an angle, right? So this focal length is not the same with so if you take the focal length this way and then the focal length here might, if it's at an angle, would be different.
Okay.
Yeah. So if you're just taking the pinhole camera model as a standard, this is how it's really generally given, with a single focal length, because it's derived with these like what do you call it, equal triangles and stuff like that. You can't really represent distortion in this diagram, right?
Yeah.
because our derivation is all done with these equal triangles and stuff. But MATLAB gives us two focal lengths for more complicated camera modeling. I've like there is no real like I've looked this up several times what to do with them if you're using it in the pinhole camera model, and I think the best we can do is this. I mean, also the values are very comparable to each other, so I think we should be fine. Your other option to deal with the fact that we have two is to basically, if you want to just use one, maybe just use an average of the two.
Okay.
It's not going to make a huge difference in the final result. For example, if I say
If you just invert like f
Yeah.
prime.
yeah, if you just do the same, I mean, you'll get roughly the pixel values that similar pixel values.